why I should be getting cementite and perlite. Very difficult. Look at the phase diagram, follow the law. Okay? Okay, again this. Alright. One way to have very good strength for your steel is what? You know, perlite is a what? Eutychon reaction, formed by Eutychon reaction. Perlite is what? Very strong. Are you clear now? Try to have a structure with as much perlite as possible. Okay? Perlite, perlite is strong. Now, have I explained this diagram to you before in the lab? Those of you who do heat treatment with me, we have done this, isn't it? Alright? Then, okay? Here, this one, this is the what? DBT diagram. DBT stands for what? Time, temperature, transformation. Okay? Right, now, this line here is known as MS, martensite start. This one here, MF, martensite formation finish. Okay? Down here is what? Perlite. Here is what? Bainite. Anything below here, over this side is what? Bainite. Down here is what? Martensite. Here is what? Austenite. So here should be what? Austenite plus what? Martensite. Okay? Here should be what? Austenite plus what? Alright, here should be what? Austenite plus what? Bainite. Alright, now, you know when you do heat treatment, after you austenitize, if you cool in air, air cooling is very slow, isn't it? You cool very slowly. What do you get? Perlite. This one here is what? Normalizing. Very slow cooling. If I quench in water or oil, what do I get? Martensite. This one here is what? Hardening. This is how you use your what? DET diagram. Are you clear? No? Okay? It will show you, that you cannot use a very slow cooling rate. If I use a slow cooling rate, okay, I will get what? Perlite. Very fast, you will be hardening. Now, what if your cooling rate is not fast enough? Something like this. You know, some of you who do the what do you call it? Water, no, the 1050. You quench in water, but you cannot harden. Correct, no? You cannot get 50 RC. Some of you, in fact, most of you didn't harden the steel. Why? Because you need to actually cool it very fast to fully harden it. So, if let's say your cooling rate instead of like this, okay, is like this. So, can you see from here to here you'll be getting somewhat perlite. Okay, from here to here you are getting what? Martensite. So, for this cooling rate, I will be getting what? Perlite plus what? Martensite. It is not what fully hardened. Your cooling rate is what? Not fast enough. Are you following me or not? If your cooling rate is even slower, then it becomes what? Normalizing. You need to have a what? Very fast quench rate to give you what? Hardening. Okay? Okay? Now, martensite is formed because when I quench, okay, the carbon actually must come out. When there is no time for the carbon to come out, you will be what? Trapped inside. Then it becomes what? Instead of forming perlite, in perlite, your austenite is supposed to change to what? Ferrite. But at the same time, the carbon will come out as what? Cementite. That's why you get your perlite. Are you clear? Ferrite and cementite coming out at the same time. So if your cooling rate is very slow, can you see? You will get what? Ferrite. Okay, one layer ferrite. That means your austenite is supposed to change to what? Ferrite and cementite at the same time. But if you were to crank it very fast, there is no time for it's supposed to form ferrite and then carbon come out as what? Cementite. But fast cooling rate, no time for the carbon to form cementite. So the carbon will be trapped inside. Then you get martensite. Are you clear or not? You get martensite. So you must what? Crank very fast. Right? To change your austenite to martensite. Okay? So martensite, very brittle. Very hard, very strong, and brittle. Are you clear or not? Now, do you know that if I got a crystal like this, have I explained this to you in solid solution strengthening? If my crystal is perfect, then my atom can slide very easily. Dislocations can take place very easily. But if my crystal like this becomes distorted, then it will not slide so easily. So in martensite, because their carbon trapped inside create a lot of what? Distortion. Then it becomes very difficult to slide. Then your materials become very strong, difficult to deform. Alright? Okay? So the more carbon I have, the more distortion, create more distortion. So my hardness should be higher. Okay? So what do? We already spoken about this in your lab, you do tempering. Okay, you allow the carbon to come out. When the carbon come out, the distortions will reduce, so your material will become what? Less brittle. But you sacrifice hardness. Alright? That is called tempering. Okay.
Sir, is this one reversible?
Tempering is not reversible.
No.
Hardening is reversible. You can redo hardening. You can redo normalizing. Because why? Basically, if this is an iron carbon diagram, okay, for hardening, all this, you are actually austenitizing. That means you start all over again from austenite. From our heat treatment processes for steel, the first thing you do is what? Austenitizing. Remember or not? I told you, heat to 3830. Then after that, depend on your cooling rate, you get different processes. So you can redo all those, Alright, but tempering is what? Tempering is below 723, You don't get any austenite below that. Okay? Okay, I think some of this I'm going to cover here already. I listed here. Hardening and strengthening. Okay. Okay. There is a difference. Take note of this between dispersion hardening and precipitation hardening. Precipitation hardening is due to what? Precipitation. Dispersion hardening is due to what?
Diffusion.
Solid particles to add in time. Just like your concrete. What do you add inside?
Steel.
Okay, so when the crack moves, that is dispersion hardening, that is dispersion hardening. The precipitate will disperse all over the material, you know. So when I have a crack, when the crack comes to the same particle, it will stop there. You clear up? Whereas for precipitation hardening, the hardening mechanism is due to what? Tell me. It's due to what? We talk about aluminium, you know. It's due to what? It's due to, like solid solution hardening, it's due to distortion in your crystal lattice. Okay, I repeat that again. Dispersion hardening is due to solid particles. So when your crack encounters solid particles of structure, but precipitation hardening is due to your crystal lattice becomes what? Distorted. When it becomes distorted, it's very difficult for what? Atoms to fly. Okay, so it becomes stronger than that. Are you clear? Okay? Alright, now can you read all these up yourself? Okay? They are very simple. I summarize for you in here. Okay, this picture will go very clear. Okay, now I mentioned to you that dispersion hardening is due to what? Solid particles. So sometimes in your materials you can actually add alloy elements to form what? Compound. These compounds are actually what? Like solid particles, you know, inside. So this becomes known as, they will act as a what? The obstruction. Alright. Now, the intermetallic compound can also cause distortion in your crystal lattice. It depends. You know, if it is very big, it becomes known as what? Dispersion hardening. If it distorts your crystal lattice, it becomes known as what? Dispersion hardening. Okay? Alright. Okay, so this one here, how do you strengthen? How? If I ask you a question, you know, aluminum silicon alloy, how do you strengthen? How? You look here, what do you have? I can do very good. This is now all modification. It's on here. How you do modification? How?
Sodium.
You add sodium. That is provided what? You are having a what? Hypoelectric alloy. Hypoelectric alloy what? Whenever you do it for, because it is already this type of structure. So you do what? Modification. Okay. What else can you do? Actually, I can refine the grain, isn't it? Refine grain. How do I refine grain? How? Fast moving grain, add grain refiner. We have done this before, isn't it? What else? Here, what do you notice? I have got what? I have got what? Alpha. What is alpha? What is alpha? Alpha is what? Alpha is a solid solution. So I can add alloy element to strengthen alpha. If my alpha is strong, overall you can strengthen alpha. Are you clear with that? Okay? So alpha is a solid solution, so I can do what? Solution what? Solid solution, now I can call it solution strengthening. So you can do all these type of things. Are you clear now? Alright, to increase the strength. Okay, now, okay, this is important. Look at this. Alright? I have got this side here, coherent precipitate. This side here is incoherent precipitate. Which one gives you more distortion? Which one? Coherent or incoherent?
B.
Huh? A or B?
B.
B. And B is what? Coherent. Coherent precipitate is part of the matrix. You know matrix is the body, you know, the aluminium. Okay? So coherent precipitate is part of the matrix. Are you clear? Over here, can you see incoherent precipitate? It then becomes independent. Can you see that? It has its own what? Grain boundary. It has its own surface. Can you see that? This one here. Alright, now, when you do heat treatment, you know, we talk about this aluminum heat treatment over here. Can you see that? Alright? You must do what? Aging. You must do aging. Okay? Now, when you do aging, alright, the precipitate will start to form. When it first starts to form, it is part of the matrix, so it is not coherent. As this coherent precipitate grow bigger, alright, it will create more and more distortion. So you find your strength will what? Increase. But if you keep on doing, it will grow and grow until eventually it will start to form its what? Grain boundary. It becomes what? Independent. Once it becomes independent, you lose the distortion. Are you clear now? So it becomes what? Over-aged. That's why you are what? Your strength will start to drop. So are you aware in your experiment, when you do your aging, your strength will go up, then after that come down. Did you get that results? You cannot keep on going to the moon, you know. Alright, you go up and then after that you will come down. Did you all get that? Have you already started plotting your graph?
Haven't finished yet.
Or your specimen is still in the refrigerator? Okay, you have that aging, you know, you what? Coherent, then after that what? Incoherent, you drop. Are you with me? You can see diagrams of this now. Okay, so this one here, we have redone. Your heat treatment is what? Two parts. The first part is what? Solution treatment. Okay? Where you must heat above what temperature? Solver's temperature. Then after that you quench. When you quench, what happens? You get a what? When you quench, what happens? You get a supersaturated solid solution, which is what? Unstable. Alright? And this supersaturated solid solution is so unstable. To become stable, it must give off, you know, if it's supersaturated, it's unstable. Even for liquid, supersaturated is also unstable. You will always want to give out the what? The excess. Alright? So in this case, after solution treatment, you have to be very careful, you know, because room temperature also it can age. Are you aware about that? Aging at room temperature. So what do? You put in the fridge. So that because it needs energy, you know, for the what they call atom. So you put the fridge, no energy. Okay. So after that you do aging. Are you clear? When you do your lab report for aluminum, which actually I'm not involved in that experiment, but that experiment was written by me. Alright? you better use this. Are you clear enough? In your report to explain. You know the theory one? This will be useful. This diagram. When you want to explain, you know, the process. Okay? Hey, this diagram here, 12.4, is this the diagram you gave me just now?
Yeah.
This is the one. Okay, so is it? I already explained the steps now. Alright, it's 3, 4 here. Okay, in fact, this one, actually, I think it's all from your book, but I summarize it for you in 1 or 2 PowerPoint slides. You read, you grab it, then you read very simple. Okay? You see, all the important things are mentioned. What are the important things you must mention? Saturator, supersaturator, solvers, you know, when, all these other things, you know, you must mention. Okay? Okay, Okay? This one already done. If you understand this, then you know what you are doing for your experiment. Right? Yeah? Are you all clear now? This is the explanation for your experiment. This one, I think you will tell you, if you do material in more detail, in all precipitation, the precipitate when it is formed, the time will go through all these stages. Are you clear enough? Okay, but I won't ask you this. Just to let you know, you know, precipitation actually is a mechanism. You will go through all this, right? This diagram here, in your experiment, you can plot this graph. Do you have enough point to do this? Don't have. Just actually, your okay, you know, your experiment, right? You can actually do 2 things now, right? That means you have got fixed time. When you got fixed time, you'll be using what? Different what? Temperatures. You see that? Okay? So here will be your, let's say, tensile strength or your hardness. You will notice that you should be getting different temperatures. Alright? 6 times. So this one here will tell you to whichever way. This one is to roughly tell you for using this time what would be the best temperature to use. Right? You may go up. Alright? Then for this time here, for this temperature here, it may restart to what? Over 8. You get me, right? The other one will be what? Fixed temperature. That means here will be your high. Alright? And then here again tensile strength or your what? And then here of course you can then you will notice that okay, if I use high temperature, I will achieve my maximum very fast, but after that I will also come down very fast. If you use a lower temperature, it takes longer to achieve the optimum, but then longer, but your optimum is what I will usually have achieved. Alright, so you can have what? T1, T2, T3. So usually I should think T1 is more than T2 is more than usually the case. Very fast ratio, maximum, but very fast come down. If your temperature is high, then you can have what? Natural aging. Natural aging will take a long time. Natural aging. Okay, long time. Okay, so if you look at this slide here, alright, it basically gives you an idea about aluminum alloy. You know, you use this for rivets, you know, the body, the sheet metal work, sheet aircraft, you use this aluminum copper alloy rivets. When you need to deform it a time, it must be in the solution treated of the rivets. So if it is solution treated, it is a solid solution, supersaturated. Alright, you will be what? Very soft, very you can deform it very easily. So, you know, rivets needs to be what? Needs to be what? Deformed. Right? After that, you have to what? Go through aging to strengthen it. So, alright, at first, then you must go through the what? Aging. This aging must be what? You must do it properly. Alright, natural aging is okay. But when you do artificial aging, it is very easy, you don't control. It becomes what? Overage. What is the cause of overaging? What is the cause of overaging? In a nutshell, your precipitate becomes what? Incoherent. Remember? The precipitate at first is what? Coherent, it will grow and grow and grow and grow until you reach a certain size and it becomes what? Incoherent. That is what? Over-aging. So if you do artificial aging where you are using what? Heat, there's a risk, alright, if you don't control your parameters, then you can over-age. So your experiment is basically for what? Experiment is basically for what? To tell you what is the best temperature and time. But solution treatment, no problem right now. Just, you know, the receipt what? Just read it out. Okay, that's all. But aging, correct, needs more control. Okay? Can you see at the back? Are you okay to see at the back? Okay, now I need to use two diagrams for heat treatment. Okay, first is the what? Phase diagram. Right? I can also use the what? You can call it CCT, continuous cooling transformation. Right? Or it can also be known as what? TT, time temperature transformation. Now, your phase diagram is something like this. Okay. Just now early on I draw this also, isn't it? Alright. What is this? This is 0.8. Usually steel, when you use steel, the carbon content is normally less than 0.8 because less than 0.8, your steel is a what type of steel? What steel? Hypoelectric steel. Hypoelectric steel contain what? What do you have here? Here is austenite, Here is austenite plus what? Cementite. Very hard and very what? Brittle. So your steel not very good for general application except maybe what? For what? When you need what? Wear resistant kind of application, you know, because the carbide give you the wear resistance. So usually when I do heat treatment or whatever it is, the general type of steel is what? Hypoelectric. Where what you use in the lab is 10150. The 50 here stands for what? Your carbon content is what? 0.5% carbon. Alright? Now, the first thing I need to do is I heat it up until 830 degrees centigrade. I will be here, austenite. That is known as what? Austenitizing. Are you clear now? That is known as austenitizing. Then, after that, okay, I come to this one, TDT diagram. Some people call it CCT. CCT stands for what? Continuous cooling transformation. TTT stands for what? Time temperature transformation. Okay? Over here, you know, just now I have already done this for you. Alright? Here is what? Alright? Here is what? Button side. Alright? So, once I austenitize, and okay, hang on. One more. Over here is what? B stands for what?
Barnite.
B stands for what? Bainite.
Barnite.
Okay, B stands for bainite. So, once I austenitize, okay, and then can you see this one here is what? Air. Alright? I get what? Perlite. So this one here is what? Huh? This one here is what? Okay. This one here is quench. Okay. It will be what? Hardening. I end up getting what? Hardened. Okay? And what about this? I will bring it to here. Here is austenite. Okay? And I will hold it until I come to here, which is all bainite. Then after that, I pull it. I will end up getting bainite. This is actually what? Austenite. Okay? I can also do this. I quench, I hold, but I don't let it go in. I don't let it go in, because when I go in, I will start to get what? Bainite. I am still getting what? Up here, you see, this line here is your MS. As long as you are above it, you will be what? Austenite. Okay? And then after that, I cool. See, will I get martensite? I don't get martensite. Okay? And this is known as what? Okay? But for you to do all these processes, you must first heat up to what? Austenitize your steel first. Can you see it now? Change it all to like, because you must start from what? Austenitize. Then you do this. So for heat treatment, you can refer to what? These two types of diagram. Okay? This is theory. Don't get carried away. Because in practice, if you know what type of steel you are using, the information is available. You know, you don't even have to wait refer to this diagram. You tell you what temperature, then use what to and for how long. All the type of things. Are you clear now? Okay, now this one here, I just want to quickly run through it, right? Not go okay. Process annealing. You know, if you take a piece of wire, you keep on stretching it through a die. make it smaller, smaller in diameter. Or you take a piece of steel, you keep on rolling it, it becomes better and better. As you deform more, your material becomes harder. Why? Because there's going to be more distortions in your crystal lattice. Very major, isn't it? When it distorts, then it becomes more difficult to deform, slack or enter slack. This is known as work hardening. So what do you do? If I have a piece of, I want to do wire, I can keep on drawing, it becomes harder and more brittle. So it becomes very unproductive and dangerous to keep on carrying, isn't it? It may even break because of brittleness. Are you clear now? So I must do this. I send the piece of steel to the furnace, right? I heat it up. But my heating temperature will be less than 723. Because why? I just want this to take place. I want the distorted grain to recrystallize. That means new one will form. Okay, and the new one will grow, taking over atoms from the old one. So I end up getting my grain will be very EQS. It becomes soft. After I done this process annealing, then I can continue to grow of the wire. Okay? The second one is full annealing. If let's say you take molten metal, you pour it into an ingot mold, you form an ingot. And then if you were to section the ingot, you find that the macrostructure is very horrible. The grain, very coarse, and then we talk about problems like coring. Remember coring and all those? You appear in all these, Okay, those type of structures. So you take this ingot, alright, you send it to the furnace. You austeritize it, okay, then after that you cool it. Then all these grains will become more uniform. Full annealing, the difference between full annealing and normalizing is this. Alright? Full annealing, when you austeritize, you must austeritize. After that, your cooling is important, isn't it? You let it cool inside the furnace. That means it's very slow. You just switch off the furnace power. But normalizing, what you do is you take a piece out, you let it cool in one hand. So which one is faster? Normalizing. The faster cooling rate will give you final grain size. Okay? So if you want final grain size, you do normalizing. Okay? Now, what is this periodizing anneal? We are saying that if your over this side here, if my carbon content increase, my cement type becomes what? Cement type becomes what? More coarse. There are cement type thing. Cement type is what? Iron carbide. Very hard. So when I do machining, I will have a problem. Okay? You can do a heat treatment known as what? Periodizing anneal. Okay? Where the cement type, instead of being in the form of a blade, it will round up to become what? Spherical. So when I do machining, it becomes what? Easier. My cutter can go through the, instead of blade, it can go in between the sphere. That is what? Periodizing. You will improve your what? That's what you with high carbon content. Then I have got hardening. You know what hardening, right? Basically, hardening, what is the microstructure you are getting? Hardening, what microstructure? Martensite. Steel hardening, you get martensite. okay, which is what? Very brittle. So what do? You must what? Do everything. This is our experiment. See how we got through all this. Okay? Alright, so I will not describe it anymore. You can refer to your PowerPoint. Okay, this one we have done. Okay. Okay, here. Now, you know, if you look at this diagram here, when I do heat treatment after quenching, you know, after quenching, I would expect my austenite to change to what? Andesite. Okay, but if your steel has got very high alloy element content, after quenching, you can still get some austenite left. These are known as what? Retained austenite. Are you clear now? Okay? Now, retained austenite is very harmful for various reasons. Number one, martensite is what? Very hard. Martensite. Austenite is what? Very soft. So if my steel has got retained austenite, I will not get what? Maximum hardness. Affect my hardness. Number two, okay, when austenite change to martensite, room temperature, is austenite supposed to be stable at room temperature? No. It is supposed to be exist as what? The steel, either pearlite or what? Martensite. So, this austenite has a tendency to change to what? Martensite. Are you clear or not? When it changes to martensite, the volume is bad. So, if my steel has got retained austenite in it, when this austenite change to what? Martensite, my volume will increase. So, I will not have what? Dimensional stability. That means my dimension is unstable. Are you clear or not? Okay? The austenite, retained austenite can anytime change to what? Martensite. When it changes, my dimension will be affected. So, if you talk about precision, that will be a problem. Okay? The third problem is this. When retained austenite change to martensite, quite often I get cracking taking place because why? The newly formed martensite is what? Very highly stressed. Easy for it to snap. Alright, so can you repeat for me what are the three problems? Number one is what? Number one is what? No? Okay. Your hardness will be what? Lower. Very good. Number two? Your dimension will be dimensional instability, not stable. What is the third one? Tendency